And the practical op-amp integrator, if I just draw down how it looks like, is we are adding additional resistance, and we call it RF, like that. So even though this guy gets disconnected, we still have a bypass to keep this feedback loop. So let's keep it like this. We can find the transfer function by considering this as one element and this whole thing as a single element that is being connected like this. Okay, here's a single element that is being connected for the feedback loop. And let's call this guy as ZF, and this guy is ZS. And the transfer function we got previously is ZF over ZS, right? And ZF, first ZS is nothing but that's just a resistance, right? So the impedance of this element is just RS. So that's a no-brainer thing. And the impedance of this parallel element is going to be RF parallel CF, right? And that is going to be 1 over RF plus J omega CF. You know, the parallel thing is 1 over R1 plus 1 over R2, this kind of format, right? So that is just applied here, 1 over R, and ZF is actually 1 over J omega F, CF. So we do another 1 over, so that becomes just a single number. So the impedance of this feedback thing is given as this whole equation, and the impedance of this guy is just RS. So what do we have to do? We have to just plug these in back to this equation we got, and that is H of omega equals negative RF divided by RS, 1 plus J omega RF CF. And one assumption we make when we add this RF value here is this RF is much greater than RS. That's an assumption we make when we create this feedback resistor to make as a practical op-amp integrator. So let's now try this low frequency and high frequency analysis just one more time. Here, remember, we talked about what if the input is a very low frequency, what if the input was a very high frequency, and we got infinite and 0. And this infinite was a problem because we cannot realize that, right? And let's see if this practical solution of adding additional resistor solved that problem. So if your input frequency is a DC or very small, that means omega is almost like 0, right? So if you plug 0 in here, that's going to be 0. This guy goes away. So now what's left? We have RF divided by RS. And what if we had a frequency that is infinite? This guy is now infinite. So this whole thing is infinite and it's just a number. So it's 1 divided by infinite. That is going to be 0. So now we can clearly see that this part was the problem, and now it's being solved. See? This was the problem. We cannot realize infinite in real life in low frequency, but now by adding additional resistor at low frequency, we have a value that is limited. It's RF over RS. So it's going to be, depending on your choice. If you select this to be 10 and this is 1, then that is just a ratio of 10, okay? And this is something similar to what we saw before. It's a low pass filter, right? In the low frequency, your output to input ratio has some value, but in the high frequency, that's going to be 0. That means everything is kind of blocked out, right? So it's a low pass filter. And in the low frequency, it's not going to be infinite anymore, not AOL, but you have a specific value, and that is called DC gain. And this RF over RS, that is going to be your low frequency value. So if we draw this thing one more time, the Bode plot, then this here is the previous ideal case, right? It's a straight line going down. But we talked about this part is the problem. We cannot realize this very large infinite gain. So by introducing that resistor, what we have here now is the low frequency thing is chopped down. It was a straight line going down from here, but now this is not there anymore, but we have a saturated value, and then it starts to bend down, and it follows the ideal, that straight line going down. If we write this down, the value at this point is going to be, we just found out that here, when we have a frequency that is very low, this amplitude ratio is going to be RF over RS, because you take a look here, the frequency gets to 0, so this whole thing goes away, and just this guy is left, right? RF over RS. And we are taking a look at the magnitude of that, so this negative thing is ignored. So RF over RS. So the value at this point is RF over RS, and that is going to be 20 times log base 10, right? Because we have converted that into decibel scale, okay? And it starts to bend at a frequency, the cutoff frequency, and there is additional frequency that is called 0 dB frequency when this line crosses the 0 dB, okay? So now we have two frequencies. One is when it starts to bend down, and the other one is when it crosses this 0. And let's just write that down first, and then I'll explain what those means. So the cutoff frequency is going to be 1 divided by RF CF. And the unit of that is radian per second. So if you want to convert that into hertz, you have to divide by 2 pi, okay? And the 0 dB frequency, which is this guy here, and that is when your H becomes 0 dB, or that value is 1. Think about it. 20 log base 10 of 1 is going to be 0 dB, right? Because whatever, if your log it has 1, then that means this is 0. So that's 0 dB, or the ratio is 1, okay? And that frequency is 1 over RF, RSCF. SCF. All right, and again, that is in the unit of radian per second. So then let's talk about the meaning of these two. So cutoff frequency is the same as our previous RC circuit. It's when it starts to bend down, okay? And this 0 dB thing means it's when the frequency has the input to output ratio that is 1. So H magnitude is V out over V in, right? And that is 1. That means the V out magnitude is same as V in magnitude. You see? So this frequency is when your output amplitude becomes same as your input amplitude. And what would happen above this frequency? Your output amplitude is going to be smaller than your input amplitude, right? You see what I'm saying? Above this frequency, your output amplitude is going to be smaller than your input amplitude. But below that frequency, your V out is going to be greater than V in. Got that? So this frequency, you generally don't want to use that, because think about it. Your goal is to get the integrated signal, right, of VI. Okay, so your goal is to find the integral of VI. But what if your output that you getting is tiny compared to your input? That's not good, right? You want to have a decent amount of voltage coming out. So if you select frequencies that is above this, your output is going to be smaller than your input. So that is not really recommended, okay? So for the integration purpose, we are going to use the frequency between here and there, okay? So if omega C is having this kind of relationship, then V out is integration of V in, and V out is greater than V in, okay? When omega is V out is the integrator of V in, that's the same, but V out is smaller than V in. So we want to use this frequency range because we are getting the output integrated and the amplitude is greater than your input. So the frequency range you may want to use is here. Then what about this area? What about these frequencies? You're not going to use these frequencies because think about an ideal integrator. So if it follows this kind of line, that means your output is being integrated like ideally. So you're going to get a clean integrated signal. But what happens for the practical case? Your practical output is following a line that is different from the ideal case. That means your practical integrator is not giving you an integrated signal. So frequency below that, the out is not integrated if the frequency is below that thing. You see what I'm saying? Ideally, it should follow this kind of line to be integrated. But your practical response is giving you something like that. So it's obvious here and there, they're different. That means ideally it should be integrated, but your output in your practical case is not being integrated. So you don't want to use a frequency range that is from 0 up to your cutoff frequency, okay? And you should use the frequency that is above this cutoff frequency, but below your 0 dB frequency, because even in this area, it is being integrated. Because take a look, your practical response, the black curve, is same as your ideal blue curve, right? So your practical response is same as your ideal response, which means it's being integrated. So here, everything is being integrated, but this part we don't want to use because your output is getting smaller and smaller. It's integrated, but it's a tiny signal coming out. Why would you like to use that tiny signal, right? You want to have some kind of decent area like here. So This is the frequency range you want to use to have your output integrated, and your output is decently large enough. And if we talk about this bullet point here, if your input has a lower frequency compared to omega C, which is here, then the circuit will work as an inverting amp, not an integrator. So you don't want to use this frequency range to have your signal integrated. And on top of this, more practically speaking, if you have that luxury of choosing the frequency range, I would recommend choosing from here to there. This is 10 times of your omega C, and that's omega 0. So if you have a luxury that you can choose a frequency range for integration, this is the best frequency range to use for integration. And the reason why is, even at this omega C, let's take a look around here. Like, well, my drawing is maybe misleading. Let me just correct my drawing. Okay, so we have an ideal line like that, and this black curve is the practical. And how I expressed why we're not using this is the ideal curve and the practical curve, it's totally different. So it's not being integrated. What about this here? I told you this area is okay to use, but still they're close, but it's not close enough. But after you get a little bit higher frequency, they are really converging, and it's almost identical from there. So that's the reason why, if I have the luxury to narrow down my frequency, then I'm not going to use this frequency as well, because they are close enough to be integrated, but still there's a discrepancy. But after about like 10 times of your omega C, if you go even higher, then from here it's almost identical. So this frequency range between 10 omega C and omega naught or 0 dB frequency, that is going to be the best range to use for any integration. But if you have to live with the right range, then you will want to pick from omega C up to omega naught. But do not use this frequency range. Got that? So let's try a very simple example here. We have RS is 10K, CF is 10 nanofarad, and RF is 100K. Well, we don't have that diagram here, but let's assume these are the numbers. And our input was a sine wave that had 5,000 hertz, 5 kilohertz. Then we would like to find what our V out is for a given configuration of R, C, and R values. So for that, step number one is to check if the excitation frequency, the input frequency, 5,000 hertz, is in the suitable range of integration. The suitable range is from here to there, right? So we would like to see whether 5,000 is between these two values. So the cutoff frequency FC was 1 over 2 pi RF CF. And if you do the math, it's going to be approximately 160 hertz. RF is 100K, CF is 10 nano. So you just plug those in here, and that is going to be about 160 hertz. And for a proper integration, the excitation frequency, or the input frequency, should be greater than 10 times of FC, which is 1/600 hertz. I'm talking about this point here. If we had the luxury to pick a narrow range, but that provides a best result, this is the frequency you want to pick, and that's 10 times of your omega C or your FC, and that is happens to be 1600. And let's check what is the 0 dB frequency is, and the 0 dB frequency in hertz is 1/2 pi RS CF, and if you do the math, that is 16 kilohertz. So we got 16 kilohertz, and this is 1.6 kilohertz, right? So 10 times of FC was 1.6 kilohertz, right? And 16 kilohertz is our F naught. That's the range we want to use, and our 5K just fell between those two, right? So this between 1.6 and 16 is the suitable range. It's here. This is 1.6 and this is 16, and 5K just happened to fit between those two, right? So from here we can conclude it's suitable for integration. So once we know that it's going to be integrated, then the next step is just to find what that output voltage is going to be. It's just the integration of your input, right? So if we use the equation that was provided in the previous page, and that is going to be, we assume this to be 0, and that is -1 over, what's RS? RS is 1K, right? So 1,000 times CF. CF is 10 nanofarads, so that's 10 nano, which is 10 to the 9, right? And we need to find 0 to t of sine of 5,000 hertz, right? So sine 2 pi 5,000 t dt. From now, it's just math, right? So this is going to be, and that is going to be, after you do the math, it's going to be 3.18 cosine pi t. So if we had an input that was a sine wave of 5,000 hertz, then we're going to have a cosine coming out with a different amplitude, but the same frequency. It's going to be 2 pi at 5,000. Okay? So what we're having is, we're having something like this. So that's our V out, and the black line is our V in. We have an input that's a sine wave with an amplitude that is 1, right? It's just a sine wave with amplitude 1. So this is your sine wave going in, and your output is going to be having an amplitude of 3.18. So this is going to be 3.18 here, and it's a cosine, so it's a cosine wave like that.